Okay, today we'll look at stoichiometry. We've definitely covered some stoichiometry in first year chem. We've studied a little bit of that in the summer assignment, a little bit in the fall. But here are some typical kind of questions you're going to get in AP. And also, we're going to go through a couple of the problem-solving techniques I think you can use. So we definitely have factor label. So writing all your units out, making sure everything crosses except for what you want in your answer. And we've maybe briefly touched upon if you have a limited reactant question, we can use something called an ICF table. And ICF table is going to give us our initial amounts of chemical. Any changes that occur in the chemical reaction, reactants lose amounts and products gain. And then F is final, what we're going to end up when we're all said and done. These would not be questions, this wouldn't be something that you would want to use unless it was a limited reactant question. And then this will set the table for us for when we get a little bit later on in the year when we start talking about equilibrium, and we'll use something very similar to these ICF tables called ICE tables. So instead of final, we have E is equilibrium. So here would be an example of where you could use this ICF idea. Do you have to use it? No. Is it easier to use? Yes. Before we actually get into it, when you use these ICF tables, you need to convert whatever was given to you into moles. If you had atoms, you could actually still use ICF tables. If you had molecules, any particles, because Avogadro's number is directly related to moles. But if you were given grams like this question, you have to convert that to moles first. If these were gases, which they are in this question, and it was at standard temperature and pressure, we could also use volumes in there. So we could use volumes, moles, or particles. Typically, though, we're going to convert to moles. So the question we got here, limited reactant question. 8 grams of both hydrogen gas and oxygen gas are allowed to react. So I think these are your kind of steps that you're going to want to go through to make sure you can answer this question. One, we definitely have to have a balanced chemical equation. And I think if we go to the next slide, I have some of this done for you already. Yeah, so we have to go way down here, and here is your balanced chemical equation. And I've given you the ICF in our table, and let's talk about where these numbers come from. So it was told to us that we had 8 grams of both chemicals. So I converted both of those into moles. I'll just give you a sample of one of these here. 8 grams of hydrogen gas, factor label style. Okay, so I already did the grams to moles conversion for you. And it's down here. So we start off with 4 moles of hydrogen gas, and the 8 grams of O2 that gets converted to 0.5 moles of O2. And of course, we start off with 0 products. Now you have to decide which item is going to be the limited reactant. So let's pretend for a second that whoever had done this question did this incorrectly. So let's just say that you think the hydrogen gas is the limited reactant. By definition, then, you would have to use it all up. And also, that would mean you'd have to subtract 4 from the initial amount of 4. So if you have a 4 for hydrogen gas, and it's a 2-to-1 ratio between those two chemicals, the change has to reflect those coefficients. So a 2-to-1 would be the same thing as a 4-to-2. Well, can you subtract 0.5 minus 2 and get an actual number that's not negative? You can't. So if you go down that road and you end up getting a final moles that is a negative answer, you know you've done something wrong, and just reconsider what you thought was the limiting reactant. So let's go back and do this over again. So if someone considers the oxygen gas as the limiting reactant, by definition, you have to have none left at the final. Therefore, you'd have to subtract all of your initial amount. And then again, it's a 2-to-1 ratio. So whatever number you put for the limiting reactant change, it would have to be, in this case, double that, which that is double. And so 4 minus 1 is 3. So we didn't look at the products yet, but the reactants, hydrogen gas, we have 3 moles left. And oxygen gas, we have no moles left. So again, I think we're deciding that oxygen is the limiting reactant and hydrogen gas is the excess reactant. Okay, so now how do we get H2O here? So again, we start off with 0, and then we're going to add products you would add. And how did you know to put 1 there? Because it's a 2-to-1 to 2 ratio. So wherever you have a 2, you have a 2. That means that the change has to reflect that 1-to-1, or in this case 2-to-2 ratio. So if we have a 1 change there, we have to have a 1 change here. Did we have to look at those two? No, we could look at oxygen gas. And oxygen gas is a 1-to-2 ratio. So the change that occurs with O2 when you get over to water has to be double that. And 1 mole is definitely double 0.5. So that pretty much would answer most of our questions. The only thing it doesn't answer is if you needed to know something about grams. Those are moles. So I think I have a couple more parts here. One of the parts of the question was how many grams of water can be produced. Well, we can convert 1 mole into grams, and that's 18. And then if you wanted to know how much excess reactants left over as far as mass, you'd have to convert 3 moles of hydrogen gas into grams. Okay, so let's take a look at some stoichiometric questions that would be multiple choice, and then later on I think we'll do a few free responses here. Okay, so it's a 1-to-5-to-8-to-1-to-5-to-4 ratio. Anytime you have any stoichiometric questions, it's definitely going to have something to do with the balanced chemical equation. The number of permanganate ions that react must be equal to which of the following? So again, it's a 1-to-5-to-8 ratio. How did I know it's only going to be those 3? I don't actually. I guess it could be any of these, but it's a 1-to-5-to-8-to-1-to-5-to-4 ratio. So let's look at the first one here. 1/5 of the iron plus 2 ions. So if you only have number of permanganate ions that react must be equal to which of the following? It's a 1-to-5 ratio, which is 1/5 of, it would have to be 1/5 of what iron plus 2 is. So we already grabbed an answer that's correct. Hydrogen. It's going to have to be 1/8, not 8 times, because it's a 1-to-8. It's not an 8-to-1, it's a 1-to-8. Iron plus 3. Again, it's a 1-to-5. It's not a 5-to-1. So this would have to be 1/5. And then water, 1/2. Well, I don't even know how they're coming up with anything that deals with a factor of 2. It's a 1-to-4 ratio. So we've already identified our right answer there. Next one, we have 6 moles of propane and 20 moles of chlorine gas. After the reactants have been totally consumed, how many moles of HCl have been produced? So I'm going to rewrite this down here in terms of the ICF F. And I'm only going to write the things, the components that are going to be part of this question. I, C, F. If you wanted to write the C3H4, Cl4, you could do that, but it's insignificant for this question. So we have 6 of the propanes and 20 of the chlorines. So we're going to have to subtract and we're going to have to add. By the way, you had 0 initially of the HCl. Now we have to decide which one's going to be the limiting reactant. Let's give this one a shot. So you need something that totally runs out. So it's a 1 to 4 ratio. So if you have 20 for the Cl2, you need 1/4 of that over here, which is 5. Can you subtract 6 minus 5 and get a positive number? You can. So I know that I've done this correctly. So the Cl2 is the limiting reactant and the C3H8 is the excess. The limiting reactant always drives the rest of the chemical reaction. It's a 1 to 4 to 4 ratio. So wherever there's a 4, you better have the same changes. So 0 plus 20 is 20. Let's cross our fingers that one of these answers is 20 moles, and there is one right there. Okay. What remains in the vessel after equal moles of the 2 reactants are reacted. So it doesn't tell you an exact number, it just says equal. So we can make them whatever numbers we wanted to. I think the easiest numbers for me to think about would be a 2 and a 2. Do you have to go with what I did? No, you don't. So let's go and try to figure out the limiting reactant here. And why is it a 2? 1 for the K for a change and a 1 for the Cl, because it's a 2 to 1 ratio. So limiting reactant for the K, we don't have any K left over. So it can't be that answer. Do we have any Cl2 left over? Yes, we do. So possible, possible, not possible. Oh, we've already canceled out the K. So I think we have our answer now without even figuring this out, because I think we have to be able to produce KCl because it's a product. So we definitely liked KCl, but of these 4 answers, the only one that we like the most is C. Okay, another question. We have sodium phosphate. You could write this net ionically, and I think you might be able to get somewhere with this too, but I'm going to leave it as full molecular. And that's going to make 2 products. That one is going to be soluble in water, and then this one is a precipitate. Okay, all 4 of these answers deal with brackets, and the question also states that it's about concentration. Brackets is concentration. So there is one of these materials that won't give us any ions. It's a precipitate. So I'm going to already cross that out. So let's try to figure out what we have here. 100 milliliters of 1 molar and 100 milliliters of 1 molar. We have an exact same amount of 2 chemicals. I don't think we need an exact number, but let's do it just in case. 1 molar is 1 divided by 1,000, and then we were given 100 milliliters, and this little factor label will give us how many moles we can put in our I, part of our ICF table. Do you have to do an ICF table with these? No, you might be able to do these in your in your head. Think about this. Okay, there's our starting amounts, and I don't really have to worry about significant figures, and even I don't have to worry about units in this case. These are all just which one's larger than another. So we need to figure out which thing is going to run out first. By the way, I think I got a little ahead of myself here. I don't think we balanced this. So without a balanced chemical equation, we're going to be in deep trouble. Okay, so there's our relationship. It's a 1 to 3 to 3 ratio. So if we have equal amounts of both chemicals and the AgNO3 has a 3 in front of it, I think that's going to be our limiting reactant. So what change is going to occur? We're going to lose, I'm going to write this in a different color here for a second. We're going to lose 1/3 of 0.1. Why is that? Because it's a 1 to 3 ratio. So whatever number happens here, over here has to be 1/3 of that. So I'm going to erase that so I can put the actual number in. Okay, I'm kind of rounding there. So 1/3 of 0.1 is 0.034, actually 0.03333 repeating. So it's going to give us 0.66, repeating. I'll just round that. Whoops. I'll just round that there. And then over here, it's a 3 to 3 ratio. So whatever change occurs there, better be the same change here. Okay. So we can either start with what we have the most of or what we have the least of. So I think what we really have the least of is we have 0 concentration of silver ions. Why? Because there's none left. And over here, we didn't make any. That's a precipitate. So unfortunately, none of our 4 answers deal with silver ions, so it doesn't help us get closer to our right answer. Let's go to the other side. Which one would we have the most of? Well, we have the ability to make sodium and nitrate. I'm going to put my coefficients on there and my amounts. And then over here, we have some sodium ions left. So that Na3, I just moved the 3 up front, times 0.067. And then we have some phosphate times 0.067. So I think what we have the most of, we have, let's go to our different color here. I think we have sodium left over, lots of it, comparable to the rest of the materials, and we made sodium. So I think sodium's got to be the last. So now we're down to A and C, and we just have to decide which one we'd like more, phosphate or nitrate. Which one has less, which one has more. Nitrate, 0.1 times 3, none left over. And then phosphate, 1 times 0.067. And I think of those two, we would have more nitrate. So nitrate has to be second, phosphate has to be first of the 3 that are listed. So that's how we got to that. I think you were presented with this question in the summer packet, but let's go over this again for sure. ICF table. Lots of words here, but let's try to figure out what's going on with these numbers. Initial moles of F2 is 8. Initial moles of Xe, 1.7. When all the Xe has reacted, so it's already telling you that that has to occur. The moles of unreacted, that means left over for F2 is 4.6. So what number would we have to subtract to get the 4.6? I think that would be a 3.4. And remember I was telling you that the change has to reflect the balanced chemical equation. Normally we have a balanced chemical equation and figure out the changes. Well, in this case, we have the changes so we can figure out the balanced chemical equation. A 1.7 to 3.4 is the same thing as a 1 to 2 ratio. And I think now we actually have our answer. 1 times 1xe is 1xe. 2 times 2 is 4. So there's our answer. I'm probably just going to walk through some of this. The answers, worked out answers and explanations are on the next slide here. But let's talk about what's going on here. So this is a laboratory question. A laboratory data table is provided. A student is given the task of determining how much iodine, let me move that up a little bit. How much iodine, I minus, is in a tablet. Okay, so the tablet isn't all potassium iodide. It has to have some kind of material that kind of keeps it all together. There's a little bit of filler. There's probably a little bit of a capsule part of it, but it does have I in it, or I minus. Tablet is dissolved in water, and then we have a 0.2 molar lead nitrate solution added. The reason that is added is so you can form a precipitate. The precipitate is filtered, washed, dried. Anytime we have any of these precipitate questions, you have to be able to filter it, wash it, and dry it. If you don't filter it, you don't separate that from the rest of the materials. You have to wash it, also part of that separation, because if you don't, some of the water actually has ions, and those ions will recrystallize in the salts on the precipitate, and it'll actually weigh more than it should. So you wash it with some distilled water, and then you have to dry it. If you don't perfectly dry it, then you're going to have some water left over on the precipitate, and that's going to add to your masses. Okay, so write a balanced ionic equation. Well, we added lead nitrate. So what part of lead nitrate could form a precipitate? The lead. And also a clue in there was this whole question was about iodine. So I think we're going to have iodine. And then I know that's going to have to be a 2 there to balance that. And it's going to make PBI2. Explain why the reaction is best represented by a net ionic equation, because those are the only chemicals that actually change composition, and those are the only ones either we're worried about or we're measuring. Everything else is along for the ride, those spectator ions. B, explain the purpose of drying and weighing the filter paper with the precipitate 3 times. So I don't know if you noticed this, but in this data table, they dried it once. Then they put it back in the oven and they dried it again, and it still lost more mass. And then they dried it a 3rd time, and they noticed that it still lost mass, but really the only number that changed was that 3rd decimal place. And the 3rd decimal place, or the 2nd decimal place, whatever the last decimal place is in a measurement, is always a guess by the instrument. So in all intents and purposes, these 2 numbers are the same number. And we always have to keep drying until we get to that constant mass. And that way we know that all the water has been evaporated off of the precipitate. Part C, in the filtrate, K plus, greater than, less than, or equal to nitrate. Justify your answer. I'm going to let you guys work on that one, and then we can look at the answers afterwards. Actually, I think we're going to do that with C, D, E, and F. So part D and E are both calculation questions. Calculate number of moles of precipitate that is produced. So we have some things about precipitate. Now, if you noticed, I said that we're going to use one of those two numbers. And it turns out that either of those two would have been perfect to use. I would bet that most people would jump down to that last one and use that. But that's the filter paper and precipitate. So we're going to have to subtract the filter paper. So 1.698 minus the 1.462 will give us the grams of precipitate. And then you'll have to turn that into moles with the molar mass from the periodic table. Once you know the moles of the precipitate, the PbI2, you could walk backwards and turn it into moles of I minus, or in this case I. And how do you do that? It's a 2-to-1 ratio. So whatever moles of PbI2 you have, double that, and that's how many moles of I you have, or I minus. And then that's moles. You'd have to convert that to grams. And then to get it into mass percent, we need the part divided by total. So the part is whatever those grams of I minus are, divided by the total. What is the total? The total is the entire tablet, 0.425. And then get a percentile times 100. And part F, if you would dissolve it in more water than you did previously, what would happen? The water is just a method to be able to get the tablet to dissolve. As long as you have enough water for the tablet to dissolve, it will not impact the grams of, or moles in this case, of the material you have in that mixture, solution, whatever you want to call it. So I don't think it's going to actually have an impact. Okay, now if you'd have tried to use 5 milliliters, that may have an impact because I don't know if you'd be able to dissolve the entire tablet in 5 milliliters. So as long as the tablet dissolves, it should be fine. Let's take a look at your answers. So yeah, we talked about the net ionic. We talked about why we use a net ionic. We talked about the drying, weighing. Actually, we also talked about the washing. I guess we didn't talk about part C. In the filtrate solution, filtrate, by the way, is the material that's down below. Here's my funnel with the filter paper, and this is my subsequent solution after the precipitate's been filtered out. And this would be an explanation associated with how much starting material we had. I think we talked about that how to get the mass of the PbI2, and then we had to turn it into moles using the periodic table molar mass. And then I also mentioned that once you have that molar mass, or sorry, not molar mass, the moles of PbI2, you can turn it into moles of I by the ratio of the two chemicals, and it was a 2-to-1. And then lastly, convert moles of I minus into grams of I minus with the atomic mass of I. And then any mass percents are part divided by total, and we talked about that, and you do have to multiply by 100 to get it in a percentile. Just a couple notes here. If for some reason you would get this incorrect mathematically, but you use this incorrect math down in your next section correctly, you would lose this point but still have an opportunity to gain these points. So keep that in mind. If for some reason you don't know how to do D when we get to a test, if you come up with any answer and then use it correctly, again, you will lose that on this point, but you will gain these points. So don't give up once you're in one of these free response questions. And then I said that I thought that using different amounts of water would have no change in the outcome here, and that's the case. Okay, and our last question. Again, we have a stoichiometric question, and I think it's good to kind of think about these in terms of ICF tables. 2 liters and 2 liters. And I said that it should tell you here that this question is in standard temperature and pressure. It doesn't, but it should. So I'm going to add that. But if you have gases that have liters, if you have other chemicals in moles, or if you have particles, that could be atoms or molecules, they are all equivalent and they can be used in an ICF table. So let's do that. It's a 2-to-1 ratio. So this would be a 1 there. Let me change that 1 there. So 2 minus 1 is 1. Over here, it's a 2-to-2 ratio. So if you have a 2 here, you better have a 2 there. And these are all going to be liters. Okay, so the first question is, what was the linear reactant? Well, the linear reactant's got to be the item that we have none of. And that would be the work that would show you why. So you can't just say it's carbon monoxide. You have to determine why it's carbon monoxide. And my ICF table does that. How many liters of excess reactant are left over? I think we have 1 liter. And then how many liters of gas are in the container after the reaction is complete? Well, we have the 1 liter, but we also made 2 liters. So 1 plus 2 is 3 liters. I'm going to move that up a little bit. And it says, does this reaction disprove the law of conservation of mass? So let's talk, what are they talking about here? Well, they're saying that we started off with 2 liters and 2 liters. So we started off with 2 plus 2, 4 liters, but we ended up with 3. So what we're really saying is, what we're really saying is 4 liters, I don't think equals 3 liters. Well, it's the law of conservation of matter. And a lot of people also consider this the law of conservation of mass. So what you'd have to do is convert that to grams and convert that to grams. And then you would notice that the grams would equal the grams. So it has nothing to do with liters having to be equal. It's about grams equaling grams. So this reaction does not prove or disprove the law of conservation of matter. You'd have to convert these to grams, and then if those two numbers are the same, reactants equaling products, then it would be law of conservation of mass would be proved.